All right. Good evening, everyone. My name is Daniel. I work as a mobile software engineer at Facebook here in London. And later, Hugo is going to join me on stage for some parts of the presentation. He's also working as an image infrastructure engineer here. And today we want to talk about image processing, and we want to talk a bit about what we learned doing really a lot of images on a lot of different devices all around the world. And we also recently open sourced a library called Spectrum, so we're going to talk a bit about that. But we really hope that besides that, the things that we talk about are very applicable to any app that you are currently working on. And images are really something I think every single app touches at some point. And as the Android community, we solved most of them pretty well already. And what we've done is we baked them into libraries. I think most of you know Glide, Picasso, or Fresco. But what's also important to know is we didn't really solve all the problems that we have around images. While consuming images that we just download and display is pretty straightforward with those libraries, there are other aspects to images. And what we're going to focus on today is basically the other side, where you create image content and you want to share it, you want to upload it, and it is a good thing to do a lot of, or do pre-processing of an image before you upload it. So why is that? This is an image I took with my Pixel device, and it has 12 megapixels. It's multiple megabytes in size. And if you, for instance, take panorama images, or you have a smartphone manufacturer who thinks it's a good idea to also put a video into your JPEG file, then you're easily talking multiple megabytes in size. And if you build your app and you happily test it, and you're going to be pretty happy what you got when you just test it on your office Wi-Fi, when you actually go out in the wild and your users use your app, and they happen to be on a 2G connection, you're facing multiple minutes just to upload one simple image. And this is something that's not unique to emerging markets or anything. It's really something every user will experience when they are on the train in the countryside or on a festival. So how do we deal with this? One thing we do is we give people an option to choose between higher quality, which means we send a bit more data, it takes a bit longer, but looks a bit better. And on the other hand, they can choose, oh, I don't need HD, I'm on a bad connection, I'm just casually sharing something, so I turn it down and reduce the quality for better upload reliability. And it's not just about the speed and the reliability. Many people are also on data plans, so they simply don't want to afford those extra megabytes just to send a cat meme around the internet. So what's actually happening when we tell or say we want to pre-process images? The biggest lever that we have is reducing the resolution. And it's so important because every time we halve the side length of an image, what we do is basically reduce the number of total pixels in that image by factor 4. So the resolution or the maximum dimension of the image has a quadratic impact, and also quadratic impact on the file size, which makes it a very powerful tool. Whereas on the other hand, if we would just change the quality setting, for instance, of our JPEG compression, then we very easily get to a quality that's not acceptable while still having a huge file to deal with. That's being easily said. If you go on this quest and you really want to process your image, what you probably find out, and we found out as well, is that's not just one easy thing to do. It's more of a long hike with a lot of stops. First thing we mentioned is we need to sample and resize that image. And Android gives us choice to subsample the image while we decode, or do precise resizing where we need a second bitmap on the heap. So finding the right balance here can be challenging. If you've done this and you ship the app, probably you get user reports back which complain, hey, my uploaded images are sideways. And that's because besides the pixel data that we have in those image files, what we also store is metadata. And JPEG files have EXIF metadata, which might indicate the desired display orientation. The same goes for color spaces. Android didn't have really good API for these until very recently, and it was just very common to completely ignore the color space of the image, drop it along the way, and you end up with images that don't look as good as they could. When we talk about the normal image, we basically have a lot of steps here. You capture it, save it as a JPEG. You open it in your app, you do some transformation. For instance, you want to crop it, you save it again, then you upload, then you compress it again, and then the server does much more things with it. And every time we do this re-encoding, what happens is we hurt the ratio between quality and file size. So what we want to do is do a lot of these operations lossless. And with JPEG, we, for instance, can do lossless cropping and rotation. So that might be something we want to add to the code that we write. And as images are such an important part of the apps that we do, there is a lot more to tweak. And with JPEG, you have a large array of parameters besides just that one Q value that you can change to further adapt it to your precise use case. And if we're there, we can just go the next step and don't say we are not happy with the one-size-fits-all encoder of the system, but ship our own JPEG encoder. And if we follow this journey in code, it's basically you start with a very easy function. You just recompress that image. Then you remember, OK, we want to resize. You copy-paste a bunch of code, try to figure out that sample size. I guess everyone who did Android has written this at least once. Then you get the user reports, and you add all the EXIF handling. And then you want to go one step further, want to do the lossless things, you want to do custom parameters. You end up writing C code. And then all this gets plugged together, and no one is really happy to work with this. So this journey can be really hard. And one thing we didn't even talk about is you don't do this once, but you do this multiple times. There's always a next mountain, the next app, the next client where you do the same thing. And we had the same problem with our apps. So we had small changes that did break very important flows, and we had no way to make sure that every place in the app uses the best practices that we know of, and we couldn't really improve what we had under the hood. So working this by feet is not really fun. So we decided to build a helicopter, which translates for us in writing an image processing library that makes this step simple. And what we did is we built Spectrum, and we announced it 3.5 weeks ago at DroidCon SF. And what we're going to talk about today is some of the bits that we use within Spectrum to make image processing efficient and easy, but at the same time, a very good and high quality experience. And Hugo's going to walk you through what Spectrum actually does.
So building Spectrum, our primary goal was to build a library that's simple to use, but also a library that's efficient and cross-platform. So let's start with simple to use. So as we've seen, image processing can be quite tedious. There's lots of little steps that can be easily forgotten or just used and have sort of a suboptimal solution. So our goal was to build a library where developers just have to think about the end result thereafter instead of having to think about all these little steps and what's the best way to the end result. So we decided to base our API of the Spectrum class on the three main image operations that we have. So first, we've got encode. So this is essentially the process of compressing a bitmap into an encoded image. The opposite process of this is going to be decode, so transforming an encoded image back into a bitmap. And one can also alter an encoded image, producing another encoded image, and that's called transcoding. So let's step back for a moment and look at that code from earlier. So with Spectrum doing all that in just a few lines of code. So I'm not going to walk you through each and every line just yet. I just want to focus your attention on the resize parameter here. So Spectrum allows for three types of transformations, as we've seen here. So first we've got resize. So essentially here you're going to provide a size that you don't want your final image to exceed. Spectrum being specifically built for images that we're going to upload will never actually upscale your image. So it's more of an upper limit than anything else. The second transformation that we can do is crop. So either you provide relative values relative to the image size, or you can also specify absolute ratio, absolute offsets that you want, defining the crop region. And finally, we've got rotate. So that's just an angle which has to be a multiple of 90 degrees. So that's for simple to use, but Spectrum was also built to be efficient. As Daniel mentioned, images can be huge, particularly when decompressed. And we have to be able to manage these quite easily, particularly in a world where we don't have unlimited RAM. So there is efficiency in the runtime, that's one thing, but there's also efficient in the image size that we generate. So for this reason, we've decided to base our JPEG codecs on the fantastic open source library MostJPEG built by the folks at Mozilla. So let's see what are the benefits. So this is a graph that plots the difference between an original image and its encoded version. So on the vertical axis, we've got its similarity factor expressed through MSSIM. So that's a score between 0 and 1, essentially the higher, the closer to its original. On the horizontal axis, we've got its relative file size expressed in bits per pixel. So the more to the right, the heavier the image. So here the goal is sort of the top left corner. We've got an image that's almost identical to its original, and that is as small as possible. So first, let's draw the curve here for libjpeg Turbo, which is pretty much the standard JPEG codec that you'll find on most platforms. So as you would expect, as the size of the image increases, its similarity score increases as well. If you look at it, it sort of boils down to two phases. There's the first phase where there's a considerable quality improvement for every byte that we invest. And then we have a second phase where we start getting diminishing returns. In the middle, that's sort of the sweet spot that usually matches a quality value of 75 to 85. So now, if we draw the same curve but for MostJPEG, we can see that it's consistently on the left top of the libjpeg Turbo curve. So that means that we can either get a smaller file size for comparable quality, or we can also optimize for quality and get a better quality for a similar file size. So for reference, depending on the image and some of the conditions, the image size improvements are between 5 and 15%, which can be quite considerable when you've got a lot of images that you're uploading. So just as with most trade-offs, though, you're very often trading something for something. This is not like a perfect bullet, a silver bullet that solves all your problems. Here in this case, the cost of being able to encode a JPEG with a smaller file size is that it takes longer to encode. In reality, when these images are destined to be transferred over the network, this is not really a problem because a smaller image, which means that you'll spend less time uploading the image. So in some respect, the longer encode time may be amortized by the fact that it takes less time to upload. And also spending less time to upload means that your upload reliability may gain from that. So Spectrum's core was built in C++, which means that we've also easily ported it to iOS. Just like on Android, we've built an idiomatic thin wrapper on top of it, making it easily usable from Swift, for instance. Spectrum was also built to be extensible. So the core library simply coordinates the flow of information by depending on codecs and behaviors that are vended by plugins. So we've bundled codecs for JPEG, WebP, and PNG, but developers are free to add support for additional image formats if they wish so. So doing so simply requires providing a compressor and a decompressor. And developers can also extend the base processing logic. Daniel will talk a bit more about this later on when he goes through the architecture. So Spectrum is also customizable. So some of the low-level configuration often tend to be overlooked by a platform-vended framework. So we wanted to keep it simple to use, but we also wanted to have a broad set of customization options. So an example of that would be, you've probably tried to encode images which contain sharp graphical content on top of it. So let's say you have a sticker on top of a JPEG or some text. Encoding images in JPEG for this will very often result in some artifacts on top of the sharp edges. The reason for this is that JPEG will sort of optimize for keeping more lumens, so brightness in the brightness information rather than the color information. And the reason for this is that our eyes are more sensible to brightness changes than they are to color changes. So this makes a lot of sense for pictures or like images taken from cameras, but as soon as we start having some sharp edges or some vector information that's been put on top of it, it means that we're going to have darker corners. So one of the things that you can do is disable this behavior, and doing so, essentially you disable the 4-to-0 chromosome sampling, which is the default, and you can set 4-4-4 instead. And finally, Spectrum is robust. So it's used in production in most of our apps at Facebook. So it encodes a lot of images every single day. It has really become a foundational piece of our mobile processing infrastructure. So now let's have a look at how you would typically use Spectrum. So the first step, you'll need to add it as a dependency in your Gradle file, much like any other dependencies. And then you'll need to create the Spectrum instance. So this one takes two parameters. The first one is a logger that will get called every time an operation is enqueued. The second parameter is the plugins that you want to instantiate Spectrum with. So in this case, we've got a default plugin that bundles all the default codecs that we provide by default. Also, because Spectrum has a lot of native code, you'll need to make sure to enable the ABI split so that you don't ship every platform-specific code to everyone. So if we look back at our example from before, where we want to upload an image that we've just taken, what are we going to need to do at this point? So here we want to prepare for the upload. So first we're going to want to resize the target dimension, as we've seen before, encode so that the resulting file size is smaller, while still keeping a universally compatible output. So how does this look like in code? So first we're going to define our encode requirement. This is what's going to dictate the format of the final image. So here in that case we're passing JPEG, might not be easy to see, but we're passing JPEG and AT as the quality. Second step is passing this encode requirement to our transcode options. And then here we're adding a resize requirement, which bounds the image to 2048 as the maximum resolution for its side length. As you may be able to see, the first parameter here, exact or smaller, essentially lets Spectrum a little bit of wiggle room so that it can optimize for more faster algorithm to resize our images. So once that's done, we pass all these to the transcode API. We specify the source image from an image source. Here it's coming from an input file. And we specify where we want the resulting image to be written to. So that's the image sync. We pass in the transcode option, and the last parameter is a call site identifier that's going to be passed on to your logs if you want to more easily identify where this particular image operation has been enqueued. And next I'm going to pass it on back to Daniel, and he's going to talk a bit about the architecture of Spectrum.
Cool. We're really just going to talk very briefly about the architecture. Mostly because I think it's an interesting blueprint if you encounter similar challenges in other domains. As Hugo initially mentioned, the main logic is really within the C++ core, and that's very good. And the Android API is just a very thin wrapper around it. What the C++ core does, it bases itself on plugins. And we already mentioned there's one for JPEG that is based on Mozilla JPEG. You could create many more plugins for different image formats. And that also is the reason why it's very modular. If we go back to our Gradle file from the beginning, if you, for instance, decide I don't need WebP support and I can save myself the native code for shipping libWebP, what you could just do is say, I just depend on the core and JPEG. And that's a very easy way how you can reduce APK size. Now, let's have a quick look how it works within the C++ core and how we make that claim that we keep it easy, but always give you an efficient way to do image operations. How it works is when a request comes in from the JNI level, we create an immutable object that encapsulates all those information. What we then do is we match it against a set of rules. Those rules are either provided by the basic library or by plugins. And basically what they do is they are sorted by how specific they are and how performant they are. So we have the more specific ones on top, for instance, lossless JPEG operations, and the more general ones at the bottom, for instance, those that can do basically array transformation but not as efficient. So a request is then matched from top to bottom, and we then take the most performant rule that can fulfill our request and instantiate a recipe. And that recipe is a way how we encapsulate the instructions that need to be done in order to create the output that's desired by the request. And that recipe will use the source and sink abstraction that we saw briefly in the API to talk with the JNI level to do all the processing that we need. And this C++ core that has all the logic makes it very easy to give the Android API, the iOS API, but also allows it to use it in a pure C++ context or add new layers and wrappers on top. For the rest of the talk, we're going to leave Spectrum a bit behind and going to talk about image formats. While JPEG is extremely popular nowadays, there are at least two image formats on the horizon which are really interesting and that I'm personally very excited about, and that's why I want to share it here. But the first one you might have seen in the Android documentation is Heave. It is basically a container that takes keyframes of the HEVC video codec. This was initially pushed by Apple with iOS 11, and Google now also supports decoding those from Android version Pi. Interestingly, the ability to encode as Heave files ships as a separate support library, which allows to encode even at previous Android versions. However, Heave and Heek come with the caveat that the general royalty and patent situation around HEVC is rather complicated. And that's why I'm personally extremely excited about AVIF, another four-letter acronym. And it does the same trick as Heave, but it bases itself on a different video codec. It bases itself on the AV1 video codec that's developed by the Alliance for Open Media. And that is a very broad industry consortium consisting of Apple, Microsoft, Google, Facebook, and many more. And what it offers is a royalty-free codec that uses modern coding tools that result in a much improved image compression performance. And when we did this with a small set of images in a small study, what we saw is that the relative file size can get down to 1/3 of an original JPEG file. Most JPEG gives us a nice win while remaining compatible with the most widespread image format, but this one has the promise to really change the standard image format that we're going to have in a few years. But AVIF isn't there yet, and it isn't shipped yet. It's currently in a phase where it's being standardized, and this process is very interesting because you can follow it on GitHub. Just Google GitHub AVIF. This is a screenshot from a recent draft. And there are also people developing efficient encoders and decoders. Back when we did that study, encoding one image took multiple minutes, and it's getting faster a lot with every week. To conclude the talk, let me quickly mention what we work here in London in our images infra team. If you have done images on Android, you probably have heard about Fresco. That's something that our team develops for displaying images. And with Spectrum, we added a second library that handles the other side, the production side of images. Feel free to check it out on libspectrum.io. I think this is all for the talk, and we now have 10 minutes for questions. Thank you all.